Good afternoon, everyone. My name is Ryan McGranaghan, and I'm currently a postdoc at the NASA Jet Propulsion Laboratory, and my field of study is heliophysics. And so 2 years ago, I gave a TED Talk on the importance of understanding our interaction with the sun. And the difference over those 2 years and now is that the message has changed a little bit. And the reason that message has changed is that heliophysics is a field that's experiencing a drastic change in the landscape of the heliophysics data system. And today what I want to talk about is first introduce just what heliophysics is and why it's so important, and then talk about the changing data landscape and how we respond to that. And so what exactly is heliophysics? Well, in a broad sense, it's a far-reaching field that essentially covers anything that talks about the interaction of a star with its surrounding space, whether that be planetary bodies or other heavenly bodies, or just the space around it in interstellar space. But for the purposes of our talk today, I want to focus on the system that we normally associate with heliophysics, and that's the solar terrestrial system. And so what we're looking at here is just a schematic that shows the different regions of this system, from the sun, where the different layers generate a rich, complex set of interactions, to interplanetary space, and then the region around the Earth known as geospace. This is the region surrounding the Earth affected by our magnetic field. And the region of geospace is very important because as the energy comes from the sun, it creates complex and wide-ranging interactions around the Earth. And the way these interactions affect each of us every day is known as space weather. So heliophysics is extremely important, but as we just saw, this is a very expansive system, and so it's difficult to study each of the pieces. And so the question is, how do we actually do this? And one way that we do this is through the NASA heliophysics fleet. We now have instruments on Earth and in space that allow us to study every piece of our interaction with the sun 24/7. And this is a very difficult system to observe. For instance, the premier instrument for studying the sun is known as the Solar Dynamics Observatory, or SDO. This spacecraft was launched in 2010, and it's constantly observing the sun at a number of different wavelengths, and it provides a rich set of information for which we study the sun. What SDO does is sends back 70,000 full disk images per day, generating up to 1.4 terabytes of data each day. And so over the course of its primary mission, from 2010 to 2015, it's generated upwards of 3 petabytes of data over that time. And so this is an immense amount of data for any one researcher, any field of researchers to really understand and generate new understanding from, new discovery from. And so this is one example of the changing data landscape. In the future, we'll have new telescopes on Earth, such as the Daniel K. Inouye telescope, which will generate upwards of 25 terabytes per day. And so this is going to only expand and become an increasing problem as we move forward in the heliophysics observatory. But as I mentioned, the heliophysics system is really everything from the sun to the Earth. And so as energy comes from the sun, when it reaches the space around us created by our magnetic field, it creates changes in that magnetic field in which energy propagates through and has drastic effects for the space around us in our near-Earth space environment. So these interactions lead to such beautiful things as the aurora, or the northern lights, but can also lead to much more drastic effects where our technologies and the way that we operate and attempt to use space are affected, and even the safety of our astronauts or people as they fly over the poles in terrestrial planes. And so it's very important to understand these energy interactions. And so what we do from that perspective is take satellites in the near-Earth space environment that are studying the next frontier of space, or the ionosphere. And so one of those missions that will be launching early next year is the Ionospheric Connection Explorer, or ICON. And ICON's task is to study this new frontier of space known as the ionosphere. And so the ionosphere exists from about 100 kilometers to roughly 1,000 kilometers. And it's a region where space weather interactions are particularly complex and affect each of the technologies that we rely on every day. And so it's extremely important to generate new knowledge quickly and efficiently from the data that ICOM will be generating. And so this is a very dynamic zone where weather from the terrestrial environment meets weather in space. And so what ICOM will do will provide global scale imaging of the ionosphere in the upper atmosphere. And so we're, again, presented with a situation where we'll have a wealth of data that we have to efficiently process and generate new discovery from. So when you think about the entire heliophysics fleet, really the picture that it paints is that heliophysics is a field that's firmly entrenched in the field of big data. And so you've heard a lot of this around the conference this week, but basically big data refers to the fact that data in terms of volume, in terms of variety, in terms of uncertainty and how each data set relates to each other is extremely difficult and complex to comprehend. And so now that heliophysics is in this new frontier, this changing data landscape, we have to understand how we must shift how we study heliophysics in order to generate new discovery. And so that's the new message that we've arrived at. And essentially, what we've been talking about and developing in this field is that heliophysics has to become a discipline that operates in between fields, bringing together multiple disciplines and operating in what I like to call anti-disciplinary space, or the space between fields. And so what I want to talk about today is how do we bring together the way that we traditionally do heliophysics science, take the existing models and the approaches that we use, and how do we bring that together in a new intersection with new forms of data-driven discovery. And so the two things that we need to think about here are how do we create this new frontier at the intersection of space science and data science. And so data science is a buzz phrase that you probably have heard a lot, but what I mean by it is everything in the data lifetime pipeline. And basically what that is anything from collecting the data to processing it and understanding it to visualizing it and communicating those data effectively. And so when we bring these two things together, I believe this defines a new frontier for us to study the field of heliophysics. So how is this being done right now? Well, one way is through new tools such as the Helio Viewer. This takes data from the Solar Dynamics Observatory, that rich set of image data from the sun coming back, and it provides those data in an approachable and quickly discoverable format. And so you can see that you can cycle through the different wavelengths of these images. You can identify interesting regions. You can go through different times. And you can really quickly approach the data and start to generate new understanding and discovery from it. And so this is one example of how the field of data science is really creating new tools and new abilities for us to better understand this system. And so the question is, how do we build on this momentum? Right now, these data science tools are few and far between and relatively crude. But I think Helio Viewer provides a good example of how to move forward. And just like we have data at the sun, we also have a rich set of data that's not being fully utilized at the Earth. And one issue that I want to talk about, and a use case that I believe helps bring data science into the field, is embracing the signals that exist around the Earth. And I think that one of the most powerful sets of data for studying the ionosphere are GNSS signals, or Global Navigation Satellite System signals. And just to introduce that, essentially, if you take a GPS satellite, the radio signals that are propagating from the GPS satellite to the Earth and back are passing through the ionosphere on each of those transits. And the important thing is we can use those signals to back out information about the ionosphere and about the space weather system and really start to study this system in a much more wide-ranging view. And the reason that GNSS signals make up such a powerful data set for the study of space weather is that they exist on a broader, on a more global scale and at a higher cadence than any other single data set that we have for studying space weather. And so what you see here is just the ionospheric pierce locations of those signals from the the GNSS satellite systems. So you can see GPS at the top, the Russian system GLONASS in the middle, and then the Chinese and European systems that are just beginning to come online at the bottom. And this is for 1 day worth of observations. And so these signals provide a rich set of data for us to discover space weather phenomena. The problem is these data are extremely underutilized. And the reason for that is that they're collected at different ground stations. They're siloed in different archives and in different formats. And it's very difficult for someone to approach these data and use them fully. And so this provides a perfect use case to bring data science tools into the field and start to use these data in a more robust and wide-ranging way. And so I just want to finish today by bringing it full circle and reiterating that heliophysics is an extremely important field of science. And in some ways, it encapsulates many of the other scientific disciplines at NASA. It affects Earth science, it affects planetary science, and it also concerns the field of astrophysics. When we talk about the solar terrestrial system, we realize that we're now in a situation where we have big data. We have large volumes and heterogeneous data that we have to better utilize to discover in geospace. And the reason that we can do that now is because of these new tools and capabilities from the field of data science that allow us to create a new frontier at the intersection of the way that we traditionally study heliophysics and new approaches going forward in the future to better utilize these data. Thank you very much.